Okay, so in this video, we will provide an intuitive proof of L'Hopital's rule in the infinity over infinity case, but first we will prove a specific instance of the more general result, and then see that we can naturally extend our proof of the specific case to that of the general result. So here is the specific case. We consider the initial limit as x approaches a. We will assume a is some real number, and we consider the ratio of f of x over g of x. The assumption is that as x approaches a, both f and g approach positive infinity. This means that as x gets closer and closer to a, both f and g are getting larger and larger and larger. How large? Arbitrarily large and always positive. If we have such a limit, we now consider the new limit as x approaches a still, but instead of the ratio of f over g, we consider the ratio of f prime over g prime. We make one more assumption, that this limit exists, and for now, given that we are considering a special case, we will assume that this limit, the number L, is a positive real number. And L'Hopital's rule states that if the conditions are met, the initial limit must equal this new limit. Now, how can we make sense of this? How can we show that this is true in a very intuitive fashion? Well, we're about to show that this consequence, this result, is actually a direct consequence of Cauchy's mean value theorem. So what was the idea in Cauchy's mean value theorem? Given two functions, we can parameterize a curve in the traditional xy plane in R2 in the following way. The first coordinate of our curve is given by g of x, the second coordinate given by f of x. And recall that in our proof of Cauchy's mean value theorem, we proved that at any point, any value x, at the point g of x, f of x on this curve, the slope of the curve at this point happens to be f prime over g prime. Already we see a connection. The question is now, we try to visualize this curve in the two-dimensional plane, in the xy plane, but what does the curve look like? Well, we have two bits of information here. Right? The first is that the closer x is to a, and again we are interested in, since x approaches a, what does this curve look like when the values of x are near a? Well, when x is near a, both f and g are getting larger and larger and larger. So both of our coordinates are tending to infinity, which means that the curve will shoot up in and further away in the upper right corner of the first quadrant. But that's not all. We have a second piece of information. Again, as x approaches a, f prime over g prime, being the slope of our curve, will be approaching a positive constant. And now pause to think about what this means. The slope of the curve is getting closer and closer to a fixed constant. Well, what kind of curves have constant slopes? Those are straight lines. So this assumption tells you that not only does the curve as x approaches a shoot up in the upper right corner of the xy plane, but because its slope is approaching a constant, the curve itself will be approaching a straight line. As we've just said, the only curves of constant slopes are straight lines. So let's focus here. Again, when x is near a, the curve will be really high up in the upper right corner of the xy plane. So let's focus the curve on the first quadrant. Now, since the first coordinate is given by g of x, this is the g-axis, and the second coordinate by f of x. This is the f-axis. Let's draw a line of slope L in the upper right corner of the first quadrant. Again, here this is not up to scale to give myself some room here. I'll draw the line, say, here. But again, here we have to assume, as we've just said, because both g and f shoot up to infinity, we're really far off in the upper right corner of the first quadrant of the two-dimensional plane. Now the curve can do all sorts of weird things early on when x is further away from a, but as x approaches a, as we have just said, both f and g get bigger and bigger. So further on the right, further up, the curve shoots up in the upper right corner, and the slope of our curve is approaching a constant. So the slope of the curve is getting closer to a constant, a fixed positive number, so the curve itself must be getting closer and closer to a line of slope L. Suppose it is this line. And this is the behavior of the curve as x gets closer and closer to a. The closer x is to a, the closer the curve gets to being a perfect straight line. Now let's take 2 points on this curve. Suppose we, instead of taking, and again let me here emphasize that we are considering the behavior of the curve near a, where a is some number. So let's take a point close to a, say y, and replace x by y, and say y is close but not that close to a, so it's not yet super close to being a straight line. Let's put the point here given by g of y, f of y. This is our first point on the curve. And now let's take a second value, now let's call it x, that is even closer to a. Again, we magnify here, but suppose y is really close to a, but we take x even closer to a. Since x is closer to a, both f and g are even bigger at x than they are at y, so then this other point with the parameter x will be further to the right and up, say here. So this is the point given by g of x, f of x. And now we can consider the slope connecting these 2 points, namely the average slope of the curve from the parameter y to the parameter x. We can connect these 2 points with a dotted line. And of course the slope of this dotted line is the change in f over the change in g. So change in f over the change in g. The change in f, of course, is f of x minus f of y. Over the change in g. Similarly, g of x minus g of y. And this is where things get interesting, right? From parameter y to parameter x, this is now the average slope of the curve, and now we can apply Cauchy's mean value theorem, which states that given the average slope of a curve between parameters y and parameters x, there must exist at least one point c between y and x such that the average slope of the curve is equal to the instantaneous slope at c. And now we're getting closer. Remember, both y and x can be taken as close as we want to a. So we took y really close to a, but x even closer to a. Since y can be taken as close as we want to a, and same for x, c, for any choice of y and x, c will always be between y and x. So as we let y and x get closer to a, c being in the middle will also, by this squeeze theorem, have nowhere else to go but be getting closer and closer to a. But as if you replace x by c here, as c gets closer to a, f prime over g prime at c gets closer to L. So this will be approaching the number L. We're very close except for where is the f of x over g of x coming from, right? Well, we can extract it from the average slope. If we want to get f of x over g of x, factor f of x from the numerator and g of x from the denominator, and let's see what we get from this. If we do so, well, if you factor f of x on top, everything else now will be multiplied by x. To offset this, you have to divide everything by f of x, so you'll get 1 minus f of y over f of x. And we can do the same thing on the denominator. We can emphasize g of x by factoring it. And we have left 1 minus g of y over g of x. Let's put these two together. So f of x over g of x times the new fraction, the second piece. So 1 minus f of y over f of x over 1 minus g of y over g of x. So we have here what we wanted, f of x over g of x, but we have this annoying second term. And here is the last bit of the proof. Remember, y and x were taken really, really close to a. What if we take y really, really close to a? So this result still holds, right? As y gets closer and closer to a, y will push c onto a. So we're still okay here. So what if we take y really close to a and then fix y? Let y be constant and then let x vary closer and closer and closer to a. What's going to happen? If we fix y, f of y and g of y are constants. But if we let x approach a, f of x and g of x tend to infinity. And so each ratio here, as we fix y and let x get closer and closer to a, is of the form a constant over infinity. A constant over infinity. And this is the crux. So we fix y, but we let x approach a. Here in this case from the left, same argument from the right. As we've just said, by fixing y, f of y and g of y are constants. Both f and g, by assumption, at x are going to infinity as x approaches a. And so we have a constant over infinity in each case. And so each term will be approaching 0. And look at that. By letting x approach a and fixing y, this term will be approaching 1 times f of x over g of x, so the whole thing can be made arbitrarily close to the initial ratio f of x over g of x. And now we can go back and we have our connection. By fixing y and letting x approach a, f of x over g of x can be arbitrarily close to this term, which is the average slope. But since we took y super close to a, c had to be also very close to a. The average slope was arbitrarily close to L. And so in this two-step process, we can make f of x over g of x as close as we want to L, which means as x approaches a, f of x over g of x approaches the number L. And this completes the proof. Now let's write the general statement of L'Hopital's rule and see why our proof will actually carry over to the more general statement. Oops, result. if you ask yourself, if we go back to our special case, does it matter if f and g are positive or negative, right? Well, in our case, both f and g were positive, so we ended up in the upper right corner of the first quadrant. But what if f was negative and g was positive? Well, f would be tending to negative infinity, so we would end up in the fourth quadrant. If both f and g were negative, we would end up in the third quadrant. And if g was negative, f was positive, we would end up in the second quadrant. So the sign of f and g is irrelevant. We can have a positive or negative infinity over a positive or negative infinity. The proof will still work just the same, except we end up drawing the curve in a different quadrant. We have, of course, the limit as x approaches a of f prime over g prime. Obviously, L does not have to be positive, right? The argument carries over the same. If L is negative, instead of drawing a line of positive slope, you draw a line of negative slope. The argument works just the same. And we also can allow L to even be positive or negative infinity. If you think about this, the argument will work the same if L is infinite. Because if you ask yourself, what does a curve look like if it has an infinite slope? Well, a curve of infinite slope is also a line. It's just a vertical line. And whether the slope is positive infinity or negative infinity, it's still just a vertical line. And that's what's really interesting. If L is negative, we have a line of negative slope. The proof works just the same. And even if L is positive or negative infinity, the argument still works because then we have a vertical line. Of course, the line will move, right, because both f and g tend to infinity. But if you stay close to the curve, it will look closer and closer to a vertical line. And the argument works again just the same. So L is allowed to be any real number, positive or negative, or even negative infinity or positive infinity. And finally, if you ask yourself, well, what is A allowed to be? Well, in our initial argument, A could obviously be any real number, positive or negative, but the argument works just the same if A was positive or negative infinity. Right? If A was positive infinity, it would mean y and x go further and further to the right. Since C is between both, C also moves further and further to the right. The argument works just the same. If A was negative infinity, same argument, but now you're moving further to the left, and the argument works just the same. So A is allowed to also be any real number, or also negative infinity, positive infinity. And this is the general statement of L'Hopital's rule in the infinity over infinity case. Again, the signs are irrelevant. X can be approaching a real number, or positive or negative infinity. And the limit of f prime over g prime can be any real number, even negative or positive infinity. If we are in any such case, the two limits are equal. And again, this is L'Hopital's rule. We have already proved L'Hopital's rule in the 0 over 0 case. This is the second version in the infinity over infinity case. So hopefully, this makes the result a lot more intuitive. So bring it down to the geometry. Forget the algebra here. I'm just playing around with the expression of the average slope. Focus on the geometry, right? F and g can parameterize a curve for you. G being the first, f being the second coordinate. If f and g go to infinity, the curve shoots up in the upper right corner of the first quadrant. If f prime over g prime approaches a constant, that is, the slope of our curve is getting closer and closer to a constant, so the curve is getting closer to a straight line, and if that's the case, the average slope being close to the instantaneous slope, being close to L, but the average slope is also very close to the ratio of f of x over g of x. And so this ratio is getting closer and closer to the average slope, and the average slope gets closer and closer to L. And so you can think of f over g being the average slope of the curve, f prime over g prime being the instantaneous slope of the curve. But since the curve is approaching a straight line, both the average slope and the instantaneous slope are getting closer to each other. So in the limit, they are the same. And so hopefully, again, this makes L'Hopital's rule very intuitive in the infinity over infinity case. And again, as a direct consequence of Cauchy's mean value theorem. So I hope that you appreciate this result. I really think it is a beautiful, beautiful argument.